going to apply these. So here's third movement, encounters. So the type of movement, type of motion, this is a good quote, presented by living organisms can be regarded as containing both a systematically directed and also random component. The mathematical treatment of the statistical mechanics of the kinds of systems here taken in view may appear to threaten formidable difficulties. It is hoped that this will not altogether prevent its attack. And that's almost like a call to arms for quantitative movement ecologists. I put it up here in part because of this systematically directed and also random component. There are a lot of encounter models out there. Encounter models exist. Most of them are based on ideal free gas type collision things, where every particle is sort of assumed to be moving in a straight line until it collides, and then bounces off and it moves in a straight line until it collides. And so there isn't really a random component to that kind of movement. They're very good at having distributions on the velocities of these particles, and they obtain these nice statistical mechanical properties, and they can predict heats and temperatures of gases. There's really good models for that. But for organisms, and that's sort of the basic encounter model applied to, when in the much smaller encounter literature, much smaller movement literature in general, but they basically assume directed movements, with a few exceptions. And the exceptions are all just simulations. They simulate a little bit of randomness, and they see how that affects encounters. And so I thought about attacking this, taking up this call to arms. But it was motivated by a very practical thing, and that is salmon. These are salmon, which are, species of salmon that I've actually looked at data for. This is the Columbia River. All these little dots here are dams. And within this whole system, the dams, of course, change the river significantly. But there is a lot of predation. These animals, these are some of the main culprits. And there's all this concern about how many salmon survive, how many return. A lot of money and effort invested into sort of studying the effects of this predation. And there's lots of models predicting survivals of these salmon. And so for a long time, this is sort of beginning to change. The typical predation model was this. Survival of a salmon in some reservoir with some other things going on, time or something, is dependent on time. And this is sort of a product of, this is sort of a basic sort of chemical reaction. A bunch of things are moving around the reservoir, and their survival depends on time. But some people, these are plots from an article by Anderson, Gurarie, and Dale, have gone ahead and actually regressed survival against time. And it's kind of not that easy to tell in this plot, but basically, these fish, they migrate, from 0 to 80 hours through a reservoir, and that doesn't change their survival that much. And very few of these regressions are significant, maybe only one. Whereas distance is a much sort of stronger, so let's say the same reservoir, you see that the distance that you travel, actually this isn't a single reservoir, this is moving through a bunch of reservoirs from a bunch of different releases up the Snake River. Log of survival against distance, you see there's a stronger relationship to distance. And this has something to do with encounter rates. So what's our sort of explicit sort of predation model, encounter rate model? This thing is moving with some speed. This is a predator. There's some encounter radius area, A. And we'd like to can we write survival in terms of these parameters, the mu, the sigma, the tau, the characteristic movement parameters of the migrating fish, the sigma and tau, the characteristic movement of the predator, the density of the predators, and that encounter radius. And it turns out you can.